In this video, we're going to take a slight pit stop, if you will, on this journey through the second order wholeys. And we're going to derive a result that was proven by Euler's, centuries ago. And it is not only is it a remarkably beautiful identity, but it's also extremely powerful in what it allows us to do. And it shows us how certain functions that we might think of as being completely separate and apart are actually completely related. They're kind of intertwined with each other, right? I know I seem like I'm like waxing lyrical about this, but it's just, I don't know, it's one of these fascinating results that to me never gets old. Now, the identity, it involves the complex unit, right? So I'm just going to do a little, I'm just going to say a little bit about complex numbers, not a lot, just enough that we need in order to go through and derive this identity, and then see how on earth could this be related to solving differential equations, all right? Well, let's say a complex number. So a complex number is one of the form, and we usually use like z to represent a complex number, like z and w, and it's usually of a form like this. I'll say a plus bi, where a and b are real numbers. So let me just write it together like this. So a and b are real numbers. And what is I? There are two ways you could define I. You could say that I is the square root of -1. Or you could say that I squared is equal to -1, right? So a complex number is a number that has two terms, right? The first term is just a real number. The second term is a real number times this, what we call imaginary unit, right? So this is called the imaginary unit. And it is the building block of all imaginary numbers and complex numbers, right? And so the term that doesn't have an I is defined as the real part of the complex number, and the coefficient of your I, right? The coefficient here, the b, is referred to as the imaginary part. So the real part of z, and it's usually denoted like this, Re of z, is defined to be a. So in other words, the real part of the complex number is a, and the imaginary part, so part of z, how is that denoted? By uppercase I m of z. That's defined as b. So in other words, the imaginary part of what I have here of z, that is equal to b, right? And there are lots of things you can do with complex numbers. You can do arithmetic with it. That's really not our focus here. There are entire courses where you study complex numbers, and you essentially relearn all the math that you'd have learned up to this point, but now with the context of complex numbers, right? So really what we need is this, right? Specifically this one. So what I'm going to do is, let's consider this expression. So consider the equation y equals, let's say, the cosine of x plus I times the sine of x. Right? So you might look at this and say, well, why am I doing this? Well, I mean, in some sense, I'm looking at two very, basic trig functions, but I'm now going to introduce this imaginary unit as a coefficient here, right? So instead of looking at just cosine x plus sine x, I'm going to look at cosine x plus I sine x. And I'm going to manipulate this equation. We're going to do some things with it, and then hopefully at the end, when you see where we end up, which is what Euler's identity is all about, I think you'll find it a very remarkable result. Maybe it's a result that you've already seen, but maybe you've not seen the derivation of this result. Now, again, so we're just going to treat I like it is any old constant, right? Any old constant. It just so happens to have this property that when I square it, I get -1. So the first thing I'm going to do is I am going to differentiate this with respect to x. Why am I doing this? Well, because derivatives are fun. And we're in a course now where we're studying differential equations, so I want to introduce a derivative into this, right? This equation is not a differential equation, but what I'm going to write down will be a differential equation. All right? So our derivative of cosine is negative sine. And then if I, again, just use my constant multiple rule, then this should be I cosine of x. All right? Okay, that's fine. And then what I'm going to do is, so notice this coefficient is -1. But now I have that -1 is equal to I squared. So instead of having -1 sine x, I'm just going to put an I squared in front of this. So this is where I'm going to use this definition. So I'm going to take dy dx and write it as I squared sine x plus I cosine of x. Well, now that I have an I that's common to both of these terms, I'm going to factor out an I. So when I factor out the I, I'm going to be left with I sine x and then plus cosine x. But that's kind of interesting, right? Again, so interesting that I'm going to write it a second time. So here's my I, and then I'm just going to put the cosine of x first, and then the I sine of x second. But look at this, and look at this. So after differentiating y, right, and using this new number, this I squared that's equal to -1, and factoring, I end up getting not exactly what I started with, but I times this. So what I have underlined in blue, I'm just going to replace it with the letter y. So therefore, dy dx is equal to I times y. But what do I have here? I now have a first order differential equation. So this is a first order dE, right? And it happens to be both separable and linear, right? So it's a first order dE. Again, just to identify everything, y is our dependent variable, right? And x is our independent variable, right? And it turns out that it's both separable and linear. So this one is separable and linear. Well, so let's see if we can solve this. Let's see, we've looked at methods. We've looked at both of these methods, right? Now, in terms of separable is probably a little bit easier to work with. So let's go ahead and do that, right? So I'm going to separate this. I'm going to divide through by y and multiply by dx. So I'll end up with 1 over y dy is equal to I dx. Right? Now let's integrate this. So integrating both sides, well, over here I'll have my natural log, right? And then over here, I'll have I times x plus my constant of integration, right? So if I do e, right? So if I take e and raise it to the power natural log of y, and then e to the power of I x plus c, and then also use our nice trick for exponentials where we can factor this as e to the I x times e to the c, but e to the c is just a constant, so I can write this as e to the ix times c1. Well, what do we end up with? Well, on this side, we're left with y, because our e and ln are inverse functions. And on this side, what do I have? c1 e to the ix, right? Now, going back to where we started, remember this was the expression that we wrote down, that y is equal to cosine of x plus I sine of x. Notice that when x is equal to 0, y is equal to 1, right? So notice that, when x is equal to 0 here, y is equal to 1. So then I can actually use this to figure out what c1 has to be. So over here, using this information, 1 there, c1, and then I have e to the 0, so that's c1. So therefore c1 is equal to 1, which means y is equal to e to the ix. That is pretty remarkable, because this is where we started, right? And this is where we ended up. So we started by saying, consider this expression. Now, why did we consider it? Because we just consider things. That's what we do as mathematicians. We look at this expression and we applied all the things that we know, derivatives, algebra, differential equations, solving and so forth. And we figured out that y is also equal to e to the ix. So this gives us Euler's identity. What it is telling us is that with complex numbers now, with this special imaginary unit, e to the ix is the same as the cosine of x plus I sine of x. Right? And that is one of many Euler identities. Euler has a lot of identities. So that's basically this. And this is true for all values of x, right? Nothing that we did up here said, okay, x has to be positive or anything like this. So for all x in the set of real numbers, e to the ix is equal to the cosine of x plus I sine of x. Such a simple and a profound identity. And what this really shows is that if you think about it, you learn about exponential functions usually in an algebra class, right? And then you learn about sine and cosine usually in a trig or a pre-calc class. But many times they're separate and apart. You certainly don't study them in the same unit or section. But now the power of complex numbers is that if you allow for complex numbers, then it turns out that your exponential function is simply, essentially a linear combination of cosine and sine functions, right? And you can go either way. You can take exponentials and write them in terms of sine or cosine, or you can take combinations of sine and cosine and combine them into a single exponential, right? Really, really remarkable result, right? Now, what does this mean? Well, let's say, so for instance, so now let's look at something like, let's say we had e to the 3 plus 5I, something like this, right? Or actually we should say not let, let's say consider, right? Well, I can write this again sort of in this trigonometric form. So I can take this complex, this exponential that's raised to a complex number and write it in terms of sine and cosine, right? So this is now equal to, again, this is just a little example. So using that property of factoring the exponential, I can write this as e to the third power times e to the 5i. And in this case now, just identifying the 5 as my x, I can write this part of it, right, as a cosine of a number plus I times the sine of that number. In this case, it would be 5. So this is e to the third power, and then in parentheses, I would have the cosine of 5 plus I times the sine of 5. And then if I were to distribute the e to the third power, then I would have e to the third power times the cosine of 5 plus I, or in fact, let me write it like this. And then we will have e to the third power times the sine of 5 times I. So what I was able to do is, if you look at this, I have this e raised to this complex number. But what I can using Euler's identity, I can write it in this form where it looks like what I wrote down originally as the definition of a complex number, where you have a real number, so this is the real part here, and then plus your imaginary part times I. So what this identity allows us to do is to take expressions that have a complex exponent, use Euler's identity, and write it in that standard form for a complex number. But notice the coefficients here, right? This is a real number, this is a real number. It's only when you multiply it by I and add them together that you get something complex, right? And the interesting thing is, there was nothing special about using 3 and 5. I could do this. I could say, well, what if I have something like, x plus yi? So in other words, if I had e to the x plus yi, that looks like this. I could do the exact same thing. I could write this now not to get a number, but to actually get a function or functions, right? It would look like this. I would have e to the x times e to the yi. Apply Euler's identity on this. So we'll have e to the x times the cosine of y plus I times the sine of y. And again, if I distribute the e now, here's the real part. The real part is e to the x cosine of y, and then plus e to the x sine of y times I. So again, this gives me a very powerful way of starting with something where I have like an exponential function raised to a complex number, and I can write it almost with, and this form is sometimes referred to as like the trigonometric form or the polar form of a complex number. So on this side, it's this strange kind of e raised to a complex number, but due to Euler's identity, I can end up expressing it in this trigonometric form, right? Now, as we wrap this up, again I want to go back to this equation, and I want to show you something that to many people is the most beautiful equation ever. There are some equations that are just fundamental. People just know them. They transcend science. So like when you think about Einstein, what do you think of? You might think of E equals mc squared, right? And there are some other very fundamental equations that define engineering and science, you know. But this equation that I'm about to derive is something that's truly remarkable. So if I go back to this, so since e to the ix is equal to cosine of x plus I sine of x, if we let x equals pi, what do we get? Right? What happens if we plug pi into this? Well, we would have e to the I pi, right? That sounds funny just saying it, but say it, right? E to the I pi. And then over here I would have the cosine of pi plus I sine of pi. But the cosine of pi we know is -1. And we know the sine of pi is 0, right? So this term here is -1. This term here is 0. So what does that mean? Well, this means that e to the negative, or e to the I pi is equal to -1. And if I add 1 to both sides, I get this remarkable equation. E to the I pi plus 1 is equal to 0, right? And why is this considered? To many, like I said, this is considered to be the most beautiful equation, right, ever. No more beautiful than this, right? So none, I should say. And why is it so? Well, it's because this single equation has the 5 fundamental numbers that define most of mathematics. You know, so you have the number 0, right? Right, which is, again, it gives us a way to quantify nothing, right? You know, when there's nothing there. Then we have the number 1, which is the basis for all counting numbers. You know, when you start to learn to count, you start with 1, and then you learn that 1 plus 1 is 2, and then 2 plus 1 is 3. So 1 is the basis for all counting. E is the base of exponentials and logarithms that make calculus so much easier, right? Differentiating e to the x and the natural log of x. And e, it's also prevalent in the mathematics of finance when you talk about compounding interest continuously. There is e. And you talk about pi. It's ubiquitous in geometry. You talk about the area of a circle or the circumference of a circle. Pi is everywhere in every circular clock face. Anything that's circular, pi is there. And then there is I, which is the imaginary unit. That is the basis for all complex numbers. And to have them, these 5 numbers, all together, all related in this single equation. If you're ever going to get a tattoo, this is what your tattoo should say. It should say that e to the I pi plus 1 is equal to 0. If I had a mic, I would drop the mic at this point, but no, I'm going to hold on to my little stylus here, and I'm going to say, well, think about this. I hope you kind of found this interesting. I understand that this is not like a core part to the course, but it in some way it is, because it now enables us to handle that third case of what to do if my my auxiliary equation has complex roots. We're going to be doing, where are we? We're going to be doing pretty much this process right here to come up with our fundamental set, and we'll be able to get 2 linearly independent functions and still use our superposition principle. So if you're dying to see what that looks like, tune into the next video. See you then.